So what's my goal in doing this project on object files? First thing, I came to LLVM, or I got involved in LLVM about 4 months ago, downloaded Clang, tried to compile something on Windows, and it complains about not being able to assemble through GCC. So I started working with Nathan Jedfords on getting the cough output working with MC, which Daniel Dunbar talked about earlier. And so then after that, I get to the point where the Microsoft's linker really doesn't fit well with the way Clang does things. And I decided that I wanted a much faster, a free, and a cross-platform linker. By cross-platform, I mean both hardware and software, operating system. Closer? OK. And so with the linker, OK, there's a whole integrated binary tool chain. So I decided, well, let's just replace all of binutils. And so for that, you need to share your code and follow the LLVM philosophy of everything's a library and embeddable. And so I came up with this. So first, so first, what is an object file? An object file is a structured collection of binary data. And this includes stuff such as the 3 standards, PE, COF, ELF, and Mach-O. And this includes translation units that the compiler outputs, the final executables, and also dynamic libraries, which are shared objects on ELF and I don't really know what they're referred to on Mac. This also includes archives, which are collections of other object files. And that's also fat binaries, such as the universal binary on Darwin and fat ELF for ELF systems. Raw binary files that are commonly used on embedded systems, which are just directly mapped into the processor, or into the memory. And then finally, I also include LLVM bitcode as an object file, because it does match all the other characteristics. Now, all these different formats provide a disjoint set of features. For example, raw binary files don't have symbols, relocations, or anything. All they have is a single segment that's of where to load. However, there's a common subset of features. And these are symbols, which eventually always point to a location in a section. This can be either defined in this object file or defined in an external object file. And there are sections which actually contain raw data, such as the text section, which actually contains executable code, and data, which contains your static objects. And there are a bunch of other sections, but those are all very platform-specific sections. And sections are in terms of what the compiler sees as when it's outputting its code. Segments are very similar to sections, except for this is what the linker and loader sees as the layout of the program in memory when the operating system loads it. The last is relocations, and this is relocations are what allow you to have undefined symbols that are resolved in other object files, because the file format doesn't necessarily know x86 assembly or ARM assembly, and relocations say where to insert the final address into the data. So now, every other feature in object files are basically based off of these 4. An example is C++ construction and destruction of static objects. Now, these must occur before main is run, and the destructors have to occur after it's run. And this is trivial for a compiler in a single translation unit that includes main, because it knows where main is. However, if you don't know where main is, then you have to somehow tell the linker to call these functions when main is run. So not much has changed with object files since dynamic libraries were introduced to SunOS in the late 1980s. We have the only current library available is libbfd, binary file descriptor, and that's about 20 years old, and it's been maintained and kept up to date. However, it still maintains some of this cruft that, well, all of the GNU toolchain has. As for linkers, we have GNU LD, which is slow and GPL. There is Gold, but that only works for ELF, and it is also GPL'd. And there's link.exe, which is slow, cough only, and proprietary. And then we have the various system linkers that only work for specific hardware and specific operating systems, and in the use cases they planned for it. So LLVM currently does support object file emission using the machine code library, which Daniel Dunbar covered earlier, but just for any of those that weren't in that talk. The machine code library handles both assembly, printing assembly code and printing out and assembling assembly code into object files. And it does this integrated into the compiler. And it currently supports Cough, ELF, and Mako. And the library is very assembler and assembly printing specific. It's not designed, and nor should it be designed for generic object file handling. So why does LLVM really need object files other than just direct object emission? And the first reason I came up with is freedom. And we need a non-GPL version 3 and non-proprietary linkers and libraries that can be embedded into tool sets. And another is cross-platform consistency. There really is no consistency across tool chains, even on Linux. The ARM and ELF tool chains have differences that are minute, but do affect what you're doing. And also the APIs that you use when writing a program to access object files. Currently, if you wanted to have your program, for example, I've done there to cache the output of a JIT in an object file, you'd have to write a different version for every format and platform, because platforms do different things with object files. And the last reason is really performance, and not only just a faster libbfd, but also it allows you to expose optimizations such as interprocedural optimizations through a shared library. In the case where you have a shared library that is an assembled object code, but in many cases you don't use that. You use that just to shrink code size and not to allow quick updates. In that case, you can do cross-module inlining and alias analysis and a whole other set of optimizations. And you can do that by storing the bit code in a section along with the object file and having a common and consistent way to access that across systems. The other one we talked about earlier is JIT caching, which is running the JIT and then storing that into an object file, so the next time you want to run that program, you don't have to load any LLVM, you just have to directly tell the system to load the binary. The last is an integrated linker, which integrating a linker directly into playing in a classical sense may not speed it up that much, because you're still, the object files are still, I mean, you save writing from disk and reading, but apparently that's not a very big deal. But what you can do is, I know somebody's working on a Clang server where you submit translation units to be compiled. And in that sense, you can integrate this linker and link as you are as you are compiling. And so when you get to the end, you have less than a second to actually finalize the linked image for quick compile, debug, edit cycles. And I really wanted to have more than just a library and a linker, but also provide a way to add link time features, features that have to be implemented at link time, which are generally implemented with a pre-linker. The example that I already talked about is constructors and destructors. But there's also C++ open methods, which I don't know how many people read the proposal for that. It didn't make it into the language. However, it would have required a changes to the linker to implement. And then link time optimization, which we already have the libraries for, but currently only works on Darwin and with Gold. So my goals when doing this library were, first is to have a purely library-based and have very little code in the actual executable project. Have a unified API for various formats, and provide access to details when needed. Because a lot of these standards are implemented in terms of the specific bits set in specific fields and specific names. Like the .pcrel has to have a special name in front of the symbol. And want to be able to provide replacements for all of bin utils for two reasons. Really, so that the library is fully developed and tested for a large set of projects, and also to provide a single tool chain, so you don't have to get your linker from here and assembler from there. The last is speed, because GNU-LD and link.exe are pretty slow. So I decided on really a two-level architecture, because there are two main parts. There's the serialization, which just does the reading and writing of symbols, relocations, sections, and segments. And then normalization, which provides a common API for all the different formats and platforms, which also uses MC for doing stuff such as disassembly and relaxation. So the low-level base library that reads and writes everything depends only on the LLVM system and support libraries, and no interpretation is performed at this point. This provides the symbols, sections, segments, and relocations. An example of having no interpretation is that in ELF, the relocation section, or relocations are represented in a section. And so at this level, that would show up as a section and as the individual relocations. And so this is useful for tools like object dump and NM, where you care about the what's raw in the object file. In the high level, I decided on normalization, because I couldn't really think of a better term for it. But this interprets the data into a common representation and provides an API for tools to use to access the data. And this layer understands and can perform relocations and layout and relaxation and disassembly and stuff like that. And an important invariant I wanted to keep at this level that you can't have at the serialization level is that if you go from the common form to all the independent individual forms back to the common form, you'll end up with what you started with. And of course, that only works if the format supports a feature. For example, a raw binary isn't going to support relocations. So how is it faster? First is zero copy. libbfd copies non-section data from the memory map files into a struct. And it does this at each backend location. For example, in the ELF backend, it stores, I think it was about 100 bytes per symbol extra data in addition to the memory map data. And so in this library, what I do is return a object that just has a reference directly into the memory map data, and along with functions in its vtable that knows how to access that data. And this lowers the physical memory usage and therefore increases your cache reuse and reduces swap file usage, which is a huge problem I had with link.exe until I upgraded my RAM or the amount of RAM I had, and your link times go from 20 minutes to 1 minute. So that's a huge performance gain. And the second is reading data a field at a time. Object file formats are generally specified in terms of C structs. And they generally specify ND alignment. However, some are kind of vague on that, and you have to reverse engineer it. So libbfd does this apparently by providing a callback and reading a byte at a time. So you have essentially a virtual function call, and you're reading a byte at a time. In this library, I've developed a set of templates that are already in tree to deal with unaligned, aligned, and different endianness access very quickly. And so if you're on x86, you're targeting x86, you're just directly writing and reading to memory. If you're on a different byte order system, you're going to have a B-swap and stuff like that. So here's just a quick example of the packed Indian specific integral, which has type defs for all the from 8 to 64-bit, big, little, unaligned, and aligned. And so here, so say you're reading in some binary data, and then on any system with any alignment and endianness characteristics, all you have to do is cast to, for example, the data is represented on disk as a little Indian 32-bit integer. So you just cast to that and dereference it, and then there's an operator that converts that into the host format at runtime. So as you can see here, the assembly generated is simply just move L, which is just a load 4 words, and then put it into the stack. And then if instead you're reading a big Indian onto a little Indian machine, it does the same read, except for it just adds a B swap. So it's very small code or very efficient small code gets generated for this. In libbfd, this is a huge number of calls go into translate this data. And the alignment works because the structures, packed Indian specific integral is a templated structure that simply has a char array inside of it. And so its alignment is always 1, but it converts the data internally. So then these can be combined into pewdie structures, which in this case, I just use the same names as just straight from the ELF standard. And ELF provides the guarantee that all fields are aligned. So you never have to worry about misaligned loads. So and then you can just use it directly as you would any other struct. Except for in this case, for printf, you're not going to call the conversion operator. So you have to force it to call the conversion operator. That's really the only difference here. So performance results. I added object file support to LLVM in which is just the symbol table dumper, which currently only works on bitcode files. So it was 2 times as fast on Linux, and it was 30 times faster on Windows against inim versus MinGW. I don't know why it was so much faster on Windows, because I'm not even doing memory mapped files on Windows, because LLVM doesn't support that in the system library yet. But I found that the MinGW tools are pretty slow. This is the current status is I've implemented symbols and sections in the serialization layer for Coff and ELF, and I'll be working on Mako. I have working LLVM inim, which is for most of the files in the LLVM tree. It's the exact same output as the GNU bin utils inim. And then I have also done LLVM object dump. And I've only implemented the disassembler function. But it was actually, it's just a few lines of code. Most of it is using the enhanced disassembler. And this doesn't provide symbol names, so you end up with stuff like call 0, which, again, Daniel Dunbar was talking about that. But I'm going to extend it to fully interpret as much information as it can to give a good user experience for that. And so currently, I'm working on getting patches into the trunk. And so any reviews on that would be helpful. And that's it.
representation for all kinds of different formats.
Yes, it's not a, it's a normalized API.
Okay, so the trick question then is, you have an API that can talk to any object file, and it can at least read, you can read into that format and then write back out.
Yes.
Could you write out that normalized format to some structure on this?
No.
Why not?
Because it is a API. I never, it's zero, there's never any copying. So when you say, give me the symbol name, it goes, you have an access, you have an object that represents the symbol. That actually just has a pointer to the memory mapped symbol table, in the symbol table header entry in the object file. Which is
string graph, right?
What?
That's string graph.
Yes, and actually I do use string graph. And so when you request that data, it goes in and looks for it and then gives you back a string graph. And similar stuff for that. So there is a lot more CPU overhead in this case because it doesn't read everything in at once and then convert it on the way. It does it every time you request it.
So I think that's a great API, but it sounds to me like it's both an API and an IR.
Well,
and so maybe a future step at some point would be to actually have the ability to serialize this back out in some way. And then you could do a lot of introspection on object files, and it could be a very interesting tool on its own.
Yeah, it's just, that would basically, because I thought about that. He was asking if there's an on-disk intermediate representation for this internal format. And I thought about that, but that's basically creating another object file format, which I don't mind if people find it useful to have a common format.
I don't know if it's useful, it just sounds interesting.
Yeah. Any other questions?
Basic activity already how many patches like what patches do you have that are really blocking what patches do you have that are blocking? Well, like what patches do you have that are
Patches. Oh, okay, sorry. What patches do I have it? Well, I posted it was actually quite a while ago. I guess I need to repost some of those updated to the tree, or to the top. But they're all in a zip file, all individually, because I used Git and just did them all individually. So it's not just one big file, it is incremental. But it's in a zip file from, I think, September that I have on the list. And I can repost those, but. Any other questions?
Will your linker be incremental?
Will the linker be incremental? That is one thing that I really wanted to have support for, is incremental linking. I don't actually, honestly, I'm new to linking and object files in general, but this is just, nobody else is picking it up, so I just decided to pick it up. But, so I don't fully understand how that works, but that is something that I do want to support. Any other questions? All right, that's it.